Hello, everyone. This is Jessica from Milesight Marketing Team, and welcome to the Milesight IoT Academy. Thank you so much for taking the time to join us. Today's webinar is called IoT Fundamentals, Everything About LoRa, LoRaWAN, and the Milesight's private D2D protocol. In this webinar, we will cover the fundamental aspects of LoRa, including its advantages, use cases, and architecture. We will also explore the differences between LoRa and LoRaWAN. Additionally, we will discuss important technical terms and their functionalities, such as LoRa modulation and demodulation, as well as the restrictions and range considerations that are crucial to understand. Following that, we will introduce Milesight D2D and its various applications. Why is LoRaWAN so popular? The first thing is the flexible deployment options that you have from a public or a private perspective. The firmware updates over the air is something that LoRaWAN supports, which is something other competing technologies do not do, and it does have its own geolocation capabilities. It's bidirectional security. One of the greatest part of the technology is actually the battery. It has long life, literally around 10 plus years, and it does depend on how you configure device, how many times you transmit the uplink. But overall, it gets really great life expectancy. The thing in most developed countries is being able to bring the coverage to areas where cellular coverage is poor or non-existent, especially in rural areas. Finally, the deep penetration. LoRaWAN is great to penetrate concrete ground. Steel and the use case that we'll talk to shortly will actually demonstrate that capability. LoRa is really complementary to existing IoT communication technologies. It's long range, but obviously at the cost of bandwidth, so it's designed for IoT use cases, which require only very little bandwidth, very small data. But that also makes it really suitable for devices that are usually in sleep. So it can basically be in deep sleep most of the time. It just wakes up when a message needs to be sent and goes back to sleep. So it's complementary to other IoT technologies, not a replacement. You can work it in smart agriculture, environment monitoring, measuring something for natural disaster prevention, and monitoring of industrial sites over long range. LoRaWAN is also really powerful in smart city use cases, monitoring buildings, and also obviously supply chain and smart metering. There are many different use cases in LoRaWAN. The versatility makes LoRaWAN really powerful. You can use it in many different verticals and areas. Now, technically to say, what is LoRa? LoRa can be used in the license-free spectrum. In every country, government provides some license-free spectrum for industrial, scientific, and medical research uses. And the license-free spectrum is not globally unified, different from Wi-Fi 2.4 and 5 GHz that is globally harmonized. LoRa is not the case. With sub-gigahertz frequencies, that means in different regions you have to use different frequencies. For end users, they don't really have to think about this because LoRaWAN has been supported in more than 170 countries where they can find all the frequencies for their own region. For solution providers, if you want to ship devices or deploy solution in different regions, please choose the right version with right frequency. Europe uses 868 MHz, while the USA, Brazil, and Australia use 915 MHz, for example. In Australia, it operates between 915 and 928 MHz, and the region codes used for software setup are either AU915 or AS923. Region code setup is often just a line of code. From that point forward, the way LoRaWAN is used is common for all devices. Now we know that every country or region has its frequency band. Each country also uses a sub-band frequency scheme to create channels of transmissions. Each sub-band is composed of a number of frequencies called channels. For example, in Australia and New Zealand, the band is called AU915. It goes roughly from 915.2 MHz to 927.8 MHz. And the AU915 is a band where there is a fixed number of channels, 64 channels for uplink, that are 125 kilohertz in bandwidth. And then there are 8 channels that are high-speed channels of 500 kilohertz, and then 500 kilohertz bandwidth again for downlink, so communication back to the end device. The United States and Australia have a similar channel scheme with 64 plus 8 uplink channels. The difference between US 915 and AU 915 is the downlink channel. Both have 8 channels utilizing 500 kilohertz bandwidth, but US 915 uses a separated band from the uplink scheme, while in AU 915, the downlink overlaps the uplink frequencies. For EU 868, it's a little different. The European regulation specifies that the network channels can be freely attributed. However, all end devices shall implement the 3 default channels, 868.1 MHz, 868.3 MHz, and 868.5 MHz. LoRa is just a modulation method, much like your classic FM or AM radio. As we all know, LoRa uses a chirp spread spectrum modulation. Modulation means how analog or digital information are encoded onto a carrier signal. The main outcome of LoRa modulation is long-range radio communication that uses very little energy. 1 to 3 kilometers in urban is normal, or 10 to 20 kilometers in line of sight. With that in mind, there are many products that simply use LoRa modulation on a single channel to send and receive data. Actually, chirp spread spectrum modulation is also used by whales, dolphins, and bats, how they communicate with their partners, how they hunt their prey. They use chirp spread spectrum. This also works over a very long distance, so that's where chirp spread spectrum comes from. And bidirectional communication also makes LoRa unique. A LoRaWAN-based network is made up of end devices, gateways, a network server, and application servers. End devices send data to gateways, that is uplinks, and the gateways pass it on to the network server, which, in turn, passes it on to the application server finally. In addition, the network server can send messages, either for network management or on behalf of the application server, through the gateways to the end devices. This process we call downlinks. The gateways can listen to multiple frequencies simultaneously in every spreading factor at each frequency. This allows the gateways to handle hundreds of devices at the same time with bidirectional communications. Then in LoRa, there is another important term, and that is the spreading factor. The best signal occurs when the end devices and the gateway are in close distance. But as we've seen, the attenuation increases as the distance increases, so the power of the received signal becomes unusable. This could be like two persons try to hold a conversation at a greater and greater distance. Now consider the same situation as a noisy party. If everybody shouts at the party, or in radio terms, all this will use the battery energy even more rapidly. An option would be to speak more slowly and clearly, and that's the job of spreading factor. A spreading factor indicates the number of data bits per second, the payload per time unit. LoRa modulation has a total of spreading factors from SF7 to SF12. The bigger the spreading factor used, the larger range the signal will be able to travel and still be received without errors by the receiver. The important point to keep in mind is that, because the communications are orthogonal to each other, multiple data rates on the same channel can be received simultaneously. And here, be mindful is a very important term, orthogonality. That's another very important term. We can easily understand spreading factors, they are invisible to each other. They are relative to each other. This means that signals modulated with different spreading factors and transmitted at the same time on the same frequency channels simultaneously do not interfere with each other. So spreading factor, they are invisible to each other. Faster orthogonality. You can see this comparison table. The distance increases. The signal is sent with the spreading factor stepping from 7 nearby to 10 or even 12 at a distance. If every communication was just allowed to follow this pattern, the whole network will be slowed down. To avoid this situation happening, there's another rule, limits the total amount of time any transmission can take, and this is just 1% of the allowable time. Short range communication, speaking rapidly, can pass more data at a higher rate against to the distant extremes. This trade off of distance against power consumption and quantity of data sent is covered by the data rate, what the spreading factor to use. And this is always your choice. No single spreading factor is always best for your use case, and that is why LoRaWAN has a mechanism called adaptive data rate. The adaptive data rate is choosing the best spreading factor in a particular scenario. For example, when end devices close to the gateway use a high data rate, lower spreading factor, they spend less time on air and exploit the low link budget that they need. For more distant nodes, the data rate is lower, higher SF, and the link budget is higher. Based on the exact situation, the network server can ask an end device to change the data rate, and that is really powerful in LoRaWAN to automatically and dynamically adjust the data rates and optimize battery life and link quality. LoRa is the unlicensed spectrum. It also has something that you need to consider as the duty cycle or dwell time. It means the certain amount of time before the signal received by the receiver. It differs from region to region. For example, in Europe there is a 1% duty cycle per day, depending on the channel. To respect the 1% duty cycle, after sending a message, we have to wait 52.47 seconds before sending a new message. In Australia, there is no duty cycle limitation applicable, and the dwell time limitation is 400 milliseconds. These restrictions are varies in different regions. Basically, in Milesight, we have set it up in all hardware devices by default. End users are not allowed to change the duty cycle. Let's see the LoRa performance range with theoretical value and the real limit in practice. What is the real range that you can get with LoRa? LoRa's theoretical maximum range is an astonishing 700 kilometers. Real-world performance depends heavily on the environment. And the long-term LoRaWAN distance world record has been broken in 2023. The new world record stands at an impressive 1,336 kilometers, about 830 miles. This achievement was made possible by installing LoRaWAN trackers on the fishing boat Estrela de Sesimbra and its buoys along the Sesimbra coast in Portugal. Guess what? 3 messages reached a gateway connected to the Things Stack community located in the Canary Islands. There is 1,336 kilometers. The remarkable point of this record is that it's achieved at sea level. Since LoRa can support the range of hundreds of kilometers, why can't you cover all of Europe or all of Australia with a single gateway? And that's obviously because free space is only in space, and on Earth we have factors like the structural attenuation. So the buildings, the trees, the materials, things like that, there's reflection and diffraction. So there are buildings with a lot of glass that reflect a radio frequency signal, and also there is a Fresnel zone. You must have a lot of line of sight paths around your devices to assure the communication quality. So your range is limited, is shortened by all of these factors. Finally, another physics aspect that's important to note, and that LoRa performs really well on this aspect, is the Doppler effect. I think you can still remember the sound changes when a police car or ambulance passing by. That's the same with this. When a device would be moving really fast away from a gateway or towards the gateway, it's changing the frequency. And LoRa has proven to be super robust also against this effect. And that means that you can also install LoRa devices on moving objects like cars and trains sometimes. So what are the considerations for bigger range coverage? It's always better to install gateways outdoors and on higher position. And there's also quite some research on this. It's really hard to say beforehand what the range of a particular gateway in a particular setup will be, because it depends on so many different factors from both environment and device itself. So the range depends on indoor, outdoor placement, as well as the elevation of the gateway, and also obviously the elevation of the end device. Summary of LoRa. You can enjoy the long range, long battery life, and easily expand the network by adding more devices and gateway. It is so robust to the electromagnetic interference, multipath fading, and Doppler effect. So it can be a really choice for IoT applications. LoRa is a radio, not a protocol. Next, I'm going to talk about something related to LoRaWAN. LoRaWAN and LoRa, they are not synonymous. So what's the difference? LoRa is the physical layer. It is developed and maintained by Semtech company. LoRaWAN is an open networking protocol that delivers secure bidirectional communication, mobility, and localization services. It is standardized and maintained by the LoRa Alliance. And in this slide, on the layer below, you can see the different regions have different bands, such as in Europe, in the US, in Australia, in Asia. There are different frequencies. Since LoRa is a radio, not a protocol, so it must work within a certain frequency range. For example, cellular phones have several reserved frequency bands around 900 MHz and 1800 MHz. The users pay for use within these bands. However, there are some specific bands that are available for low power use and license-free. 2.4 GHz is a global band that allowed for unlicensed operations, so Wi-Fi and Bluetooth can work in this band. And LoRa is designed to work in the license-free band legally in different regions. And then there's a lot of modulation, and LoRa modulation is really about transmitting data over the air in a very efficient way over long range. So that's LoRa. That's really just getting data through the air. Then in gray part, that is what LoRaWAN does. That is a MAC layer, means media access control. And in this layer, it does all the security features in LoRa, activates devices on a network, count acknowledging messages, synchronize the windows that your application can send data to the end devices, help to send commands or messages back to end devices and things like that. So the communication protocol LoRaWAN built upon on the underlying LoRa physical layer. Then on top in blue is IoT application. What does a LoRaWAN network architecture typically look like? It includes 4 components: the end devices, gateways, a remote network server, and application servers. These components are interconnected in a star of stars topology. So this is the topology. On the left, you see end devices. Sometimes we also name them as end nodes or sensors. Generally, the battery-powered devices used to detect the changing parameters such as temperature, humidity, water level, and so on. They are connected to one or more than one gateways. Actually, there's not really a connection between an end node and a gateway, not a physical connection at all. Because the gateway is basically listening for messages from end nodes wirelessly via LoRa. And the gateway is a dumb packet forwarding device. It doesn't understand the contents of the packets or decides what to send back. But the main LoRaWAN characteristic is the central role of the gateway. It receives packets from sensors via LoRa and then forward the packets over Internet Protocol to the network server using a backhaul interface, Wi-Fi, 4G cellular network or Ethernet cable connection. The network server does the packets decoding. Network server understand the contents of data packets. So the network server identifies the end device, receives multiple copies of the transmitted packets, decrypt and delete same packets, does some security stuff to protect data, and then forwards the payloads to whatever application server the end user requires. And finally, the application server. This is the final destination of data, where you can get your data to manage devices, to check the status to send messages or commands back to the sensors in the field. The application server may be on a cloud infrastructure solution like the AWS IoT or Azure. Or maybe it built using AWS services, and this is where you built your IoT applications or dashboards, etc. And another important term in LoRaWAN is the device classes. And there are 3 of them. You have class A, B, and C devices. Class A is supported by all LoRaWAN devices. And class A is that the end device can initiate a transmission, send a message at any time. This is typically used by devices like manhole cover, trash can monitoring, just several hours or even a few days to send a message, very power saving. Class B is a beaconing. Beacon is sent by the network on a fixed interval, and the end device can pick up this beacon and wake up to receive a downlink message. So Class B devices, they are in deep sleep, but they wake up on a time interval, such as every few minutes, to listen for the messages from the network. Class B is also so power saving as Class A, but it allows the network and gateway to send a message to the end device at fixed interval, even if there's a latency at most a few minutes. And then finally, Class C. It stands for continuous downlink. It means that the end device is continuously listening for downlink messages. And this allows the network to send a message to the end device at any time. These devices, they just work and don't sleep, so they use more power and are often mains powered. Class C usually works with devices like streetlights with power source, so you can turn them on and off at any time. So which type do you need? It's a trade-off between battery lifetime and communications delay. Then a few things on LoRaWAN security. Since many customers ask me if it's secure to send data over the free license spectrum, the answer is yes, definitely. There are two key elements to the security of a LoRaWAN network: the message authentication and the join procedure. The join procedure establishes mutual authentication between an end device and the LoRaWAN network to which it is connected. Only authorized devices are allowed to join the network. LoRaWAN MAC and application messages are origin authenticated, integrity protected, and encrypted end to end. So these security features ensure that network traffic has not been modified. Only approved devices are connected to the LoRaWAN network. Network traffic cannot be listened to. Network traffic cannot be captured and replayed. So you can enjoy the long range, long battery life, and easily expand the network by adding more devices and gateways in this secure LoRaWAN network. LoRa is really a global technology, so you can use LoRaWAN all over the world, either in the public network or your private network, everywhere where there are regulations with a license-free spectrum. These telecommunication companies, IBM and Cisco, are important members of LoRa Alliance, and many famous carriers have all announced nationwide deployments of LoRa networks. As you can see in the image here, LoRa has been adopted in more than 170 countries. Milesight joined the LoRa Alliance on 2019 as an adopter member, and all our LoRa-based hardware are certified by LoRa Alliance, which guarantees the smooth compatibility with other LoRaWAN devices. Finally, I'd like to delve into the private LoRa protocol developed by Milesight, known as the D2D protocol. Just as we discussed, LoRaWAN is so popular because of its long-range capabilities, low power consumption, and cost-effectiveness, but some limitations come along as well, such as not for large data payloads because it limited to 100 bytes. And more importantly, it's not ideal for real-time applications that require lower latency, because LoRa will not support the direct communication from nodes to nodes if without the use of a gateway. So all the data transmission must be processed by the gateways and network server, which cause delay. If you want to trigger multiple end devices simultaneously, for example, the lights control, well, all those end devices must be working in Class C mode to always keep their transceiver and receiver windows on, which means much higher power consumption. To resolve the latency issue, we make a new protocol Milesight D2D to speed up the communication. The technology is that we can do a device-to-device communication using LoRa with the same range. Milesight D2D protocol enables direct communication between various Milesight brand LoRaWAN sensors without the need for a LoRaWAN gateway. This protocol offers lower latency, less than 1 second response time, secure transmission, and reduced investment costs. This topology showcases how controllers interact with devices such as lights, curtains, and doors, facilitating efficient and seamless device-to-device communication. Think of D2D like the glue in our smart buildings. It's everywhere behind the scenes. With it, lights know to turn on when you walk in and turn off when you leave. and your window blinds raise or lower themselves as the sun moves. And that's just the start. D2D lets most of Milesight sensors and switches talk directly, so you get smooth, automated control without any extra wiring or fuss. Okay, that's all for today. Thanks again for your attendance. In the end, for getting the latest news about Milesight, just follow us on our social media. See you next time. Bye.